Hello, everyone. Thank you for tuning in to this Developer Live session on modernizing your apps with Kubernetes. My name is Sajan Parihar, and I lead the product and growth organization for the cloud native services of OCI. For today's session, I'll be joined by my colleague, Mickey, who is also on the cloud native services product management team, and by Louis, who works as a senior security architect with one of our customers named Sea Monster. And in this session, we'll talk about how you can design and build robust web applications using Kubernetes and Oracle Autonomous Database, and briefly touch on architectural best practices that can help you make your application resilient. We'll also take this opportunity to bring you up to speed with some of the recent updates we have made to our Kubernetes service and show you lots of demos. So let's jump in. Now, web applications can come in all shapes and sizes. You could be building an e-commerce system, an online banking solution, or a food delivery app. But regardless of the scenario, any mission-critical web app needs to meet a set of core requirements, such as security, so that you keep your end users' data secure at all times. Offer high availability with no downtime, be it planned or otherwise. Scalability, reduced latency, resiliency, and other requirements we have captured on this slide. And as you can think that there are so many ways to build a web app. And to simplify the architectural decision-making, we have laid out a set of design principles, which along with Oracle's opinionated technology recommendations, can help you simplify how you go about building your web apps and meet all the core requirements we just discussed. For app development, we recommend using lightweight open source frameworks such as Helidon or Micronaut that provide out-of-the-box support for common features like logging, telemetry, security, and configuration. Next, web applications typically need to interface with other business systems and services that might be outside of your organization. Services that are part of the web app should expose their interfaces via well-defined APIs. And for this, you should use OCI API Gateway as a single point of entry for all clients and route API requests to the appropriate service. We also recommend standardizing on containers as the deployment artifact you should use to package and ship apps along with their dependencies. Now, every web app needs to make a lot of changes. And to really meet the agility requirements, we need to automate, build, test, and deployment so that application development teams are able to roll out features quickly and reliably. We recently announced OCI DevOps, which can be used to set up deployment workflow to configure the steps your software takes going from one environment to another, all the way up to production. And you should definitely check this service out. Next, let me talk a bit about state. Now, you should keep middle tier components of your application stateless and use few persistent stores as possible. Now, any web app also uses data in different formats. Like your data could be relational, unstructured, such as XML or JSON documents, special, or maybe graph data. Traditionally, this has meant using a relational database for relational data, a document store for unstructured data, a graph database for hierarchical linked data. Now, as you can imagine, this leads to multiple databases, which gives rise to operational complexity as well as data inconsistency. To solve this problem, we recommend using a single multi-model database to store different types of data, index it, and provide ways to search on the data. The last principles are somewhat self-explanatory, but they are critically important. Now, for any mission-critical web app, you should instrument end-to-end monitoring and tracing, eliminate single points of failure through automated data replication, and implement a defense-in-depth approach to secure your whole app lifecycle. Now, let me quickly walk you through a sample architecture of a web app that uses Kubernetes to run containerized microservices and Oracle Autonomous Database for the data store. In this architecture, the request is routed via DDoS and WAF, which is like a web application firewall. When a JavaScript is executed on the browser or say on a mobile app, it will make calls to the API endpoints. Let's say we call it api.abc.com. And the request goes to the API gateway. In this case, the API gateway lies in between the external clients and the applications. It acts as a reverse proxy that routes requests from external client to the application. It also checks to see if the user has been authenticated and is authorized to really access this app. And for that, to really make sure that authorization is in place, your request is routed through an identity provider, such as OCI Identity and Access Management Service. For unauthenticated users, OCI IAM presents the sign-in page and sends a token to API gateway after the user has been verified. From then on, the requests are routed by API gateway to a front-end Kubernetes ingress resource, which is a load balance service. Now, as you can see in this picture, the ingress resource sits in the front of the backend microservices and acts as a smart router and entry point into the OKE cluster, which represents the application tier for this app. In case you're new to OCI Container Engine for Kubernetes, in short, we call it OKE. Let me give you a quick intro. OKE is an enterprise-grade container orchestration service based on Kubernetes. It provides a fully managed control plane and one-click cluster creation and upgrades to simplify your cluster operations. It's based on open standards and provides seamless integration with our container registry, which is called OCIR. It also offers flexibility in terms of supporting different CI/CD tools, so you have a choice, provides high performance and robust security. In terms of differentiation, I want you to remember three things. First, OKE offers a highly available control plane. Second, we don't charge any management fees. And third, there are no additional charges for the enterprise support. That really helps you to lower down your cost and build more without paying a whole lot for that. Over the last few months, we have released lots of new capabilities. And I wanted to call out some of the top features so that you are aware of the latest and greatest with our Kubernetes service. First, you can now create fully private clusters with OKE and have the Kubernetes API endpoint be part of a subnet in your VCN. Second, to increase the security of containerized applications, you can now take advantage of container image scanning and deployment authorization workflow. With this, you can have your container images be scanned for known vulnerabilities, sign trusted images using master encryption keys stored in OCI Vault service, and create image verification policies to prevent the deployment of unsigned images. And some of that we'll show in a demo in just a few minutes. Third, OKE also provides node and pod autoscaling and can automatically adjust node pool size, pod replicas, and resource reservations based on workload demands. Lastly, we recently added support for GPU and ARM, something that we are very excited about. So if you're looking to build a massively parallel data-intensive application, or do image video processing, or build a deep learning application, you can now do so using GPU compute shapes in OKE. We also realized that a lot of your apps will use a mix of Oracle and other ISV products. To support this, we have rather worked with a lot of our partners so that you have a variety of cloud-native tools covering security, federation, observability, software development, and so forth. With that, I'll pass it on to my colleague, Mickey, who will walk us through a demo. Over to you, Mickey.
Hey, folks. In this demo, I'll be sharing NewShop, which is a cloud-native web application built as a set of polyglot microservices deployed onto Kubernetes and supported by several OCI services. This reference app implements an e-commerce platform, and our goal is for you to use it to get started with cloud-native application development. NewShop is an open source project, and as such, you can feel free to follow the GitHub link that I have up here and take a look yourself. There are two versions of the app. One is the full-featured set of microservices deployed on Kubernetes and using OCI cloud-native services. And the second one is one with a simplified runtime that utilizes only always free OCI resources. Both options can be deployed using Helm charts, Terraform, and Resource Manager. Now that we've talked about it, let's check out the application. The application uses a public ingress controller backed by one of our OCI load balancers, and you can actually go to this URL here and navigate to check out the page yourself. This page here is intended to show the different components of the application and the ways in which they work together. On this page, you can also see the language that each component was written in. For example, carts here was written in Helidon, which is a collection of Java libraries for writing microservices. And here it connects to an orders Java application. The orders application connects to fulfillment, which is another service written using Micronaut, an open source JVM-based toolkit for building microservices. And the connection is done by means of NATS, which is a cloud-native messaging service. can see here that Go and TypeScript and other languages are used as well. In addition to the autonomous transaction processing database, which is used for data persistence, you can also see some other OCI services in use as well, including API Gateway right here, and functions, which are used for the newsletter signup. Now that we've talked a little bit about how the application is architected, I'm going to sign in and show you what it looks like. It's fairly straightforward. It should look a lot like an e-commerce application you've been to before. I've created an account, saved some payment info, and I've added an address. In this page, I can go to one of the different services. Right here, for example, I am selecting an item from the catalog. I can select the original MuMate bowl. I'll add this to my cart. If you remember, catalog and cart are both different microservices. And then when it comes time to check out, I can view my cart, trigger the checkout process, and then using the information I've already entered here, I can actually go and create an order. Nice. So now that I've done that, I'm going to go to my user and see the orders that I've already created. And I can see the one that was created with our Oracle San Francisco address. And this was created today, and we are good to go. So now that we've seen the application work, I want to go in and actually look what it looks like on the Kubernetes side. So effectively what we're doing here is seeing how it looks under the hood. The first step is going to be looking at the worker nodes that are supporting the application. Nice. So we can see here some additional details about the nodes. We can see the name, the status, the Kubernetes version, also the age. And those are the nodes on which our application is distributed across. The next thing I want to show are the different components of the application. Now, each one of these is a deployment, and a deployment is used to manage the desired state of pods, which I'll talk about in just a moment. You can see here that these are the same service names that we saw on the About page. Get a little bit more detail by looking at pods. And pods are very simply just the containers running in your cluster. So we have a variety of containers, some of which match up to those deployments, actually all of which do, some of which are still running and some of which are just used for initialization. So now that we've seen our list of pods, let's look at one of them in more depth. So for example, we can look at this carts pod. By describing the pod, I can see the containers running in it, and I can also see some other interesting information. So for example, here, I can see that this is using an image stored in the OCI registry service, which is just a Docker compliant registry. That image is called new shop carts. It's tagged with 1.5, which is the release. And I can also see some other cool stuff, like the fact that this service was instrumented to push metrics via the Prometheus format, which I can see right here. It's also worth pointing out there's a bunch of other interesting tools at work in the application. So if I were to look at the utilities namespacing again is just a different way of logically separating resources in the Kubernetes cluster. I can see some of the other things at play. So for example, there's a certificate manager in place. There's a metric server, which is used for pod autoscaling. And then also, as I mentioned before, Prometheus, which is used for metrics collection. So that's all I wanted to show on the Kubernetes side. The next thing I wanted to share was what it looks like from the infrastructure side. And in this case, the infrastructure we're running on is Oracle Cloud Infrastructure. Here I can see the parent page that includes all the different clusters that I have deployed in OCI. I'll click on the one for MuShop, which I've cleverly named MuShop app. And on this page, I can see my cluster details. So this includes cluster name, the number of node pools, the cluster version, the date on which it was launched, and also who launched it. So in this case, me. And I can also see other things like networking information. So in this case, the cluster has both a private endpoint and a public endpoint. And I also happen to know that it has worker nodes running on a public subnet. I do also have the option to make this a fully private cluster with a private endpoint, no public endpoint, and also a private subnet for worker nodes. If I travel a little bit further down the page, I can see the node pools that I have in this cluster. If you'll recall from when we were in the CLI, we have multiple nodes supporting this cluster, and all of those exist inside this one node pool. The cool thing about having multiple nodes or multiple node pools is that when they're distributed across availability domains, we can avoid a single point of failure. So for example, when one node goes down, pods will be rescheduled onto another node that, because it's in a different availability domain, will likely not be impacted by the same failures. Now, something else I wanted to show was that, if you recall, that application contains a lot of different containers, and those containers, for security purposes, are stored in our Docker compliant image registry, which is called the OCI registry service. Before we deployed our application, we stored everything there. It's very simple to do. And storing them in this system is great because it also allows us to scan those images for vulnerabilities. And it does so by comparing the images and the layers to a common vulnerabilities exposures or CVE database. So if I go to one of the images, for example, the fulfillment image, I go to one of the different tags that's available. I can see the layers that are present in the image, and I can also see the scan results. So in this case, I can see that there is a critical risk level. There were a lot of issues found. And if I want some more details on those risks, I can see what they're all related to and which specific CVEs are associated with it. In this case, maybe it wasn't the best idea to deploy this image, but that's okay, because some of my other images actually had positive results. So in this case, if I were to go to the carts application, I can see that it had no issues found. And because it has no issues found, I want to indicate to my team that that's safe and available to deploy to production. The way that I can do so is by adding an image signature to this. So because there's no vulnerabilities detected, I'm comfortable deploying it to production. And so what I was able to do is go and sign this image with an encryption key stored in the OCI Vault service. And this indicates, in this case, that the image is safe to deployment to a production cluster. On the same page, we can verify that this image has been signed. And as I see the signature here, I can see when it was signed as well. And I can also, if I'd like, go to verify that the key used to sign this image is still in existence. Also, if I decide that I'm no longer comfortable deploying this image and no longer think it's safe, I can go in and actually, if I'd like, delete the signature as well, which in this case would indicate that no longer is this image considered to be trusted. So in addition to just sort of passively indicating that this is a signed image and that it's safe for deployment to a cluster, I can more actively go and use the image verification feature, which is part of Kubernetes, to ensure that only signed images are deployed to the cluster. And so when I specify an image verification policy, what I'm doing is making sure that the images that are deployed to that cluster match one of a set of signing keys. So for example, signing key 3 in the Vault service. And if something doesn't have that image signature present, the pod, the container, the image will be prevented from being deployed to that cluster. So jumping back into command line, now that we've talked about the availability and security application, I want to show what it looks like with more load on it. This application was implemented with horizontal pod autoscaling and also cluster node autoscaling. As Saj mentioned before, horizontal pod autoscaling, or HPA, is used to create replicas of Kubernetes pods based on CPU and memory utilization. Cluster autoscaler does it in a little bit of a different way. It actually adjusts the size of cluster node pools based on workload demand. Both are very helpful for optimizing use and cost of compute resources. So as I mentioned, because we have an HPA configuration already for this cluster, we can see the different settings that are in place. So for example, here I have target utilization percentages. I have minimum pods, maximum pods that I want replicated, and I can also see the number of replicas currently in place. What I'll do next is deploy a container to generate some traffic pointing to these pods. And so all this is doing is just creating traffic and hitting one of those pods, or excuse me, hitting all of them, but in slightly different ways. The next step is for us to just sit back, wait a moment, and watch as the number of replicas is scaled up. So all I'm doing here is running that same command, just get HPA, seeing our HPA configuration, and slowly over time, you'll see the targets increase. So for example, those targets, which were very low to begin with, are now surpassing the thresholds that we've set. And if we continue to wait, we'll see additional replicas are spawned up to accommodate for that. What's really nice about this approach is that it removes the operational burden for administrators to have to go in and manually scale things on the Kubernetes level by adding replicas, or on the infrastructure level by adding nodes to a node pool. Now, it's worth noting that any good application also includes an observability strategy. And observability, in case you're unfamiliar with the term, is just a notion of being able to instrument an application or create an application that has logs, metrics, and traces, which are available to help us understand and explain the state of a system. Fortunately for me, the components in MuShop were instrumented to emit these three outputs. And in the interest of time today, I'll focus on metrics. So in addition to custom metrics available from the application and the cluster components, we can get metrics directly from OCI services at the cluster, node pool, and node level. So on that same cluster console page, I could go to metrics, see some basic metrics around unschedulable pods. I can go to node pools, drill in a little bit further, click one of the existing pools, and then see metrics related to node state and node condition. In this case, I have 3 nodes that are all active and 3 nodes that are all ready, which means that I can schedule workloads on them. If I want to go one step further, I can click into one of my nodes and view metrics. And so that'll take me to, excuse me, this is the same node state metrics, and this will take me to the compute node metrics as well. So this would be compute CPU utilization, memory utilization, disk read IO, write IO, and a number of other host level metrics as well. Now, of course, it's worth noting that if this were actually a production application, the metrics would be a little bit more interesting for us to look at. So in addition to those metrics that are available on the OKE side or from OCI directly, we also see a lot of customers using community tools such as Prometheus and Grafana, which are also available for use with OKE. Prometheus is an open source systems monitoring toolkit, which is frequently paired with Grafana, which is a terrific open source data visualization tool used to create dashboards and also alerts. It's also great because Grafana allows you to create dashboards from a variety of sources, all side by side. And it comes with a bunch of templates, which make getting started very simple. In this case, I'm using Grafana to see the usage of the carts pod that we were using before, which you'll also remember from the checkout process. And I can see the memory, CPU, and network utilization for that specific pod in the cluster. Whereas on the OCI side, we were seeing it more at the node level or the cluster level. Grafana, as I mentioned, is also useful for those side-by-side metrics. So if I wanted to create a more general view of my application metrics, including stuff like the number of running pods, the idle CPU percentages, node storage, and more, I can have them all displayed side by side here as well. And what's great about this is that it can be useful to size my cluster and also ensure that it's all running as expected. When you check out the MuShop application, you'll see that there are a bunch of dashboards created by default for you to use. Great. So now we've talked about observability. The last thing I wanted to discuss was OSOC, the OCI service operator for Kubernetes. I'll jump back into command line here. And while I do, I just want to share some details about what OSOC is and why I'm excited about it. So as you may know, container native application developers often need to connect their applications to cloud services running outside of their cluster. As we saw earlier, maybe they're connecting it to API gateway or autonomous transaction processing databases or a streaming service or something else. And as customers adopt cloud native practices, they also want to standardize those operational practices around Kubernetes. There are a bunch of different tools that you can use, of course, but a lot of folks want to control everything just simply using the Kubernetes API. So for example, in order for users of Kubernetes to connect containerized apps running the clusters to service provider services like autonomous transaction processing from OCI, they have to independently provision and manage that database by means of the console or one of the other surfaces, which can cause like a very disjointed experience. And it's disjointed because half of your resources are managed in a Kubernetes cluster and the other half are managed in OCI or via some sort of other tool. We developed the OCI service operator for Kubernetes, which I affectionately call OSOC, to be a tool that makes it easy to connect to and also manage OCI resources from a Kubernetes cluster. Customers deploy a single operator to their cluster, and that operator is used to connect to and control each of the supported OCI services. OSOC follows the CNCF standard for operators. And in case you're not familiar with the operator framework, technically speaking, an operator in Kubernetes is the combination of one or more custom resources and also controllers used to manage those custom resources. But put more simply, operators allow you to extend the Kubernetes API beyond its default capabilities. So right now, I'm going to change my context to that other cluster that we saw. And I'm going to look at the operator pods that I have deployed in my cluster. So here we see there is one that was used to initialize the operator. One right here that is the service operator bundle, which is a bundle that's actually simply used to control the operator controller manager. And then finally, the controller manager itself, which is used to watch the state of the cluster and apply necessary changes. I can establish a connection between OSOC and OCI through a Kubernetes secret. So all I've done here is just stored my OCI credentials, like my username, my fingerprint, passphrase, and a few other things like my region and tenancy. I can also see the custom resource definitions that are used to extend the Kubernetes API to control OCI resources. So in this case, I have one right here, autonomous databases. I have another one for MySQL DB systems, and I have another one here for streams. Over time, our goal is to add one for every single OCI service, at least the ones that seem appropriate, and make it so that you have a seamless experience when it comes to managing OCI resources from a Kubernetes environment. The next thing I want to show you is what a YAML file connecting to OSOC actually looks like. So you'll see here, this is the same YAML that you should be used to using with Kubernetes, but then with just a handful of additional components that we've added on. This YAML file will create a database admin password and also username. And we'll also go so far as to create a MySQL database for us. And I've specified here the compartment in which I want the database to be provisioned, the display name for my database, the shape that I want the database to run on, subnet, availability domain, and a couple of other important things like a reference to that secret file above. If I apply that YAML file, this will actually create a custom resource in my cluster and also provision a MySQL database in OCI. So literally, that was one command. That was one command, and it did not require me doing anything outside of the Kubernetes API. So if I jump to OCI and navigate to databases and then to DB systems, I should see an OSOC, excuse me, a MySQL cluster provisioned by OSOC starting up right now. Perfect. So OSOC MySQL is in the creating process. And also it's worth pointing out that OSOC can bind to existing OCI resources, such as a MySQL database I've already created. Now, as I'm wrapping up, one last thing I wanted to note is that we also design OSOC with enterprise workloads in mind. And what that means is that traditionally operators allow you to create, update, and delete resources. But when it comes to components as critical as a database, it can be very dangerous to terminate them without the proper checks. So what we've done is in the case of our database resources, our autonomous databases, and also MySQL, we've made it so that customers can delete the autonomous database custom resource, but the associated instance is not deleted from OCI and actually requires manual deletion. So we hope that in addition to OSOC being used to simplify the management of OCI resources from a Kubernetes environment, it can also be a great example for customers to follow to create their own operators. Great. So that wraps up everything from me. And now I wanted to turn things over to Louis from SeaMonster.
Thanks, Mickey. Hi, everybody. Welcome to the session. I'll take you quickly through what we did to deploy our solution onto the platform. And I'll take you through the structure of what we've got inside our solution in totality and how we made everything work together with Kubernetes on the OCI platform and the relevant services that is associated with it. The whole SeaMonster solution is built off of open source technologies that was originally intended as piecemeal pieces to perform specific functions. And in a lot of cases, they became more prevalent, more used, and some of them actually ended up being industry standards, such as the Hive, for incident response, etc. And we ended up taking the best of breed implementations out there, modifying them, making them all work together as a cohesive unit, and we deploy this on a Kubernetes cluster. The cluster consists of various pods that it's made up of either deployments or stateful sets, and these can be scaled up and scaled down as needed. The whole platform can be deployed via Terraform or Helm charts, and the intention behind this was to create a SIEM that is absolutely scalable, thanks to the metrics and the function of Kubernetes, as well as providing these services to large organizations with large flows, etc. This also brings down the cost because you can scale the system just to your needs, and it can go up and down. The stack that the system consists of is obviously a great mix of applications and languages, etc., due to the fact that it is open source projects that are developed on by various teams that we've brought together. For example, we use open source frameworks, languages and technologies we use is Node.js, Java, Python, Golang, for example. And the applications that run through that is Hive incident response, OpenSearch, and data analytics that can be run through Cortex analyzers and with open source intelligence. And you've also got the correlation engine that we use as Wazoo. The package and applications that we ship as containers can go through OKE and OCIR, and they are fully CI/CD compliant, which means that if an update is applied to the open source project upstream, it is very manageable to bring those updates into the environment, apply our own changes to the environment to make it suit our complete build, and just replace the pods as part of the live process. All of the pods, etc., can be pulled as containers directly from GitLab through Terraform or other means. And we make quite a bit of use of object storage and streaming due to the data volumes in use. Oracle Data Guard and OCI monitoring can also be used depending on customer requirements. We generally recommend that you do. And Cloud Guard can also be implemented. Data stores, in general, most of your applications that get developed in-house will have one data store. With multiple open source projects, you have to bring all these data stores together, and you have to do it in such a way that it doesn't impact the environment or the functioning of the environment. Containerization and pods lend themselves to this greatly, so it is possible to bring the individual data stores in without impeding improvements to the upstream projects, as we do contribute back to those as well. To speed up performance of the web interface, we use Redis and other web caching technologies. And to make sure that the environment can handle all the load that is pushed at it, we use OKE autoscaling and pod replication. This is a brief overview of the infrastructure design. The whole idea or concept why we decided to go to Oracle in the first place was because one of our clients wanted to run on the infrastructure, and we reviewed the Kubernetes side of things and discovered that it would be a great fit for us. This specific customer had an MSSP requirement, so with our solution and its design, we can split out the MSSP into various namespaces, meaning that each tenant or client, as such, is completely separated from the other clients logically and physically, because each client gets a full stack of the solution that the MSSP provider can then manage through a single interface. This was made possible by the cloud technologies that is currently available in the environment, and they are listed in the slide for you to review. The data is then flowed up from the client side. It can either go over HTTPS via the agent mechanisms, or it can flow over VPN tunnels that can be set up via the Hydra or appliance that we can deploy to the customer site. Everything is encrypted and secured all the way through the transport. If you require, you can even implement the SOAR automation, which allows for full API interrogation between all the subcomponents of the system, and you can automate your workflows throughout the environment. The biggest takeaways from the solution that we've built is we use the best open source tooling that's available for the SIEM space, for the red team and purple team, etc. We've greatly reduced operating costs by hosting this in the OCI environment with all the functionality and feature sets there. And there are great benefits running it in such an environment that is inherent to using cloud infrastructure, because you've got your availability areas as well as your automation with the Kubernetes clusters, etc. The cloud infrastructure has reduced deployment times greatly, where sometimes with complicated deployments, it could take up to months. This has been brought down to, in some cases, hours or just a few days, depending on the complexity that the customers want. Container deployments can generally take place inside the entire environment very quickly, because as Mickey showed earlier, you can edit the YAML configuration for the pods, which will then pull down the images automatically, which makes patching the environment much simpler and much more effective than trying to install a bare metal machine where you're running all the services. Stability has also been greatly increased, because with cloud native infrastructure, you obviously have much more capable hardware, larger scale hardware that can handle the load and impact. And you can also adjust the environment to your needs. So if you start out with low log volumes and log flows, you can always increase those to higher volumes at a later stage should you need to. That is completely at your discretion. As a closing note, it was a very brief session. The system can be deployed very quickly. The tricky part would be to define the hardware requirements that you would have up front based on the log flows, etc. The areas where you can focus on is just what you currently consume in disk storage for your logs, etc. And what your flow rates are if you currently have a SIEM. If you do not have the accurate calculations, it is not a problem. The system is completely scalable and stable. And with that, I'll hand you back to Sir John.
Thank you, Louis. Just to wrap up the session here, let me call out a few next steps for you. So if you have not used OCI, you can definitely get started easily with our Oracle Cloud free trial, which includes an always free tier. Second, you should definitely check out developer.oracle.com. There is a lot of content targeted at developers. And last but not least, the demo that Mickey showed is up there on GitHub, and I've called out the URL here.